Okay, we're starting chapter 16, which means we're starting concurrency. I'm looking forward to this. Chapter 16 with 4 sections. No, not even that long. Fearless concurrency. Handling concurrent programming safely and efficiently is another of Rust's major goals. Concurrent programming, where different parts of a program execute independently, and parallel programming, where different parts of a program execute at the same time, are becoming increasingly important as more computers take advantage of their multiple processors. Historically, programming in these contexts have been difficult and error-prone. Rust hopes to change that. This is what I'm here for. Change. Initially, the Rust team thought that ensuring memory safety and preventing concurrency problems were two separate challenges to be solved with different methods. Over time, the team discovered that the ownership and type systems are a powerful set of tools to help manage memory safety and concurrency problems. By leveraging ownership and type checking, many concurrency errors are compile time errors in Rust rather than runtime errors. Therefore, rather than making you spend a lot of time trying to reproduce the exact circumstances under which a runtime concurrency bug occurs, incorrect code will refuse to compile and present an error explaining the problem. As a result, you can fix your code while you're working on it rather than potentially after it has been shipped to production. We've nicknamed this aspect of Rust Fearless Concurrency. Fearless concurrency allows you to write code that is free of subtle bugs and is easy to refactor without introducing new bugs. That sounds like a beautiful dream. I hope it is true. It sounds like it's true, but I also have my hope is like big. So basically what they said here is that initially they thought that the making concurrency easy, safe, and not error prone was a separate problem than what they were solving with memory safety, like the type systems, yada yada yada. And then later on they realized they're kind of just one and the same problems, and that solving one kind of just fixed the other. And as a result, a lot of the errors that you would typically get in threaded programming or parallel programming, which are runtime errors, in Rust are compile time errors, which means that you learn of these errors at very different points in your life. One you learn about while you're programming and writing it up yourself, which is a beautiful time to learn about an error. And then the other one is post you writing it being tested, you feeling secure with it, it goes out to production, and then an error happened, and then you have to figure out what exactly happened. Those are the runtime errors. We don't like those. So yeah. I hope this is true. For simplicity's sake, we'll refer to many of the problems as concurrent rather than being more precise by saying concurrent and/or parallel. If this book were about concurrency and or parallelism, we would be more specific. For this chapter, please mentally substitute concurrent and or parallel whenever we use concurrent. Okay, yeah, that's a good note. Many languages are dogmatic about the solutions they offer for handling concurrent problems. For example, Erlang has elegant functionality for message passing concurrency, but has only obscure ways to share state between threads. Supporting a subset of possible solutions is a reasonable strategy for high-level languages, because a high-level language promises benefits from giving up some control to gain abstractions. However, lower-level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. Therefore, Rust offers a variety of tools for modeling problems in whatever way is appropriate for your solution and requirements. Okay? Alright, so in this paragraph, they mentioned a comparison between Erlang, but that Erlang comparison is not actually all that important. What's important here is the distinction between high-level languages and low-level languages. So what they say is Supporting only a subset of possible solutions is a reasonable strategy for high-level languages because a higher-level language promises benefits from giving up some control to gain abstractions. And this is sort of cryptic and coded, but what they're actually saying is that in high-level languages, they do things on your behalf that with the main goal of making your life easier. So in Erlang, the example they gave is that they have great message passing concurrency, but when it comes to the sharing state between threads, it's not really there. I know Python just has a lot of abstractions for you. They're just there to make your life easier. However, these things are not always the fastest thing, and they make your life easier in some aspects, but maybe not all aspects. That was the trade-off here. The sharing state between threads can't really do that easily in Erlang. At least that's how it's stated. That's how it comes across. Whereas in lower level languages, you're expected to be able to do everything. So they state lower level languages are expected to provide the solution with the best performance in any given situation and have fewer abstractions over the hardware. So seemingly what they're stating here is that Rust has to have an answer for every possible problem in terms of this chapter, which is concurrency / and or parallelism. So Rust has a bunch of tools of modeling problems in whatever way is appropriate for your situation and requirements. The main takeaway from there is just that they have their solutions for everything, seemingly, and they should be fast. Here are the topics we'll cover in this chapter. How to create threads and run multiple pieces of code at the same time. Message passing concurrency, where channels send messages between threads. Shared state concurrency, where multiple threads have access to some piece of data. The sync and send traits, which extend Rust's concurrency guarantees to user-defined types, as well as types provided by the standard library. Okay, this is going to be packed. Let's do this. Using threads to run code simultaneously. In most current operating systems and executed programs, code is run in a process, and the operating system manages multiple processes at once. Within your program, you can also have independent parts that run simultaneously. The feature that runs these independent parts are called threads. All right, getting definition of threads. Cool. Splitting the computation in your program into multiple threads can improve performance because the program does multiple tasks at the same time. But it also adds complexity. Because threads can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems such as race conditions, where threads are accessing data or resources in an inconsistent order. Deadlocks, where two threads are waiting for each other to finish using a resource the other thread has, preventing the thread from continuing. Bugs that only happen in certain situations and are hard to reproduce and fix reliably. So here they're just going over some of the issues that may occur when doing thread programming. Race conditions, which they define here, where the scenario where you have two threads that are trying to access and read data at the same time, and there are issues in the order that happens in. Deadlocks, where you can have two threads that are kind of just stuck because one is waiting for a resource and the other one is hogging the resource or trying to wait for something else so it can release this resource. It's just a bad scenario. And then the third one is just a general catch-all, some weird bugs. Rust attempts to mitigate the negative effects of using threads, but programming in a multi-threaded context still takes careful thought and requires a code structure that is different from that in programs running in a single thread. Programming languages implement threads in a few different ways. Many operating systems provide an API for creating new threads. This model, where a language calls the operating system's API to create threads, is sometimes called one-to-one, meaning one operating system thread per one language thread. Okay, that makes sense. So here they're just going over some of the ways that threads are implemented. And one model is where you have a language, it can make a call to create a thread. And this model is called one-to-one because anytime this call is made, then you have one thread that is created from it, one-to-one. One call, one thread. Many programming languages provide their own special implementation of threads. Programming language provided threads are known as green threads, and languages that use these green threads will execute them in the context of a different number of operating system threads. For this reason, the green threaded model is called M to N model. There are M green threads per N operating system threads, where M and N are not necessarily the same number. I see. So another model for dealing with threaded programs, or threads in general, is called the M to N model, and this is using green threads. So seemingly the language has their own implementation of threads. And then when you call a thread, or you call these threads, the number of these green threads and the number of operating system threads that are created because of these threads are not necessarily one-to-one. Meaning there could be, let's say, 5 here and only 2 here. Something along those lines. There's no number consistency between them. Each model has its own advantages and trade-offs. And the trade-offs most important to Rust is runtime support. Runtime is a confusing term and can have different meaning in different contexts. In this context, by runtime, we mean code that is included by the language in every binary. This code can be large or small depending on the language, but every non-assembly language will have some amount of runtime code. For that reason, colloquially, when people say a language has no runtime, they often mean small runtime. Smaller runtimes have fewer features, but have the advantage of resulting in smaller binaries, which make it easy to combine the language with other languages in more contexts. Although many languages are okay with increasing the runtime size in exchange for more features, Rust needs to have nearly no runtime and cannot compromise on being able to call into C to maintain performance. Okay, some revelations mentioned here. Runtime and what it means in different contexts. And in this context, it means the code that is shipped in your binary to help your program run. And you have languages that have large binaries. It just means the runtime is slightly larger than others. And then you have programs with no runtime, which in actuality means small runtime, because it seems like you always have to have at least a little code in your binary. So when you have the runtime like a large binary, then there's a lot of language stuff that's put into that binary that just helps your code run, other features and yada yada yada. However, Rust is in the predicament where it's not allowed to have a runtime, so the binaries have to be small, and it can't compromise by like going into the C performance stuff, like being able to call C and have C help it run its code. Let's continue. The green threading M to N model requires a larger language runtime to manage threads. As such, the Rust standard library only provides an implementation of one-to-one threading. Because Rust is such a low-level language, there are crates that implement M-to-N threading if you would rather trade overhead for aspects such as more control over which threads run when and lower cost of context switching, for example. I see. So here they're stating, by default, the Rust standard library only implements the one-to-one threading model. However, there are crates that implement the M to N threading model if you want to use those. And Some of the trade-offs are you get a larger overhead, but you have more control over when your threads run, and the cost of context switching is going to be lower. Mainly the cost of context switching should be lower because some of those threads are controlled in the language itself, like in the runtime, but not on the operating system level. Now that we've defined threads in Rust, let's explore how to use the thread-related API provided by the standard library. Ooh, we get to start. Creating a new thread with spawn. To create a new thread, we call the thread spawn function and pass it a closer. We talked about closers in chapter 13, containing the code we want to run in the new thread. The example in listing 16-1 prints some text from a main thread and other text from a new thread. All right, we get to do threads. I'm excited. Hit my editor. Use standard library thread. Thank you for spelling that appropriately for me. Use standard library time duration. Okay. Oh, I forgot to put standard library there. CD duration. And I'm gonna write this out just so my fingers get used to this. We have thread. We have spawn, which is going to create our thread. We have our closure, which takes no parameters. And then we're writing our closure. And in here we have for 1 and 1 to 10. I don't think it's inclusive, but we'll find out in a second. Print line. I'm just going to copy this part. Control copy. Hide number blank from spawn thread. Semicolon. And then we're calling thread sleep, and we have the duration passed in. How long we want to sleep for. Thread sleep duration from milliseconds. Takes a U64 and we're sleeping for 1 millisecond. That's not long. Okay, so we have that. And now in the main thread, because we could talk about 2 different threads now, main thread and then the secondary thread that we spun off. In the main thread, we're going to do something similar, but we're doing 1 to 5. And we're sleeping for 1 millisecond. Ooh, I see what they're doing here. This I can just copy. So seemingly what we want to demonstrate is what it looks like when you do things in one thread and do things in another thread, and how they kind of intertwine and jumble up. But let's verify that. Let's print this out, or let's run this. Rest threads, scope, hi, I didn't type I here. Oh, this printed everything out almost in order. Okay. Main thread, spawn thread, main thread, spawn thread, main thread, spawn thread. This is actually in order. That is kind of cute. But one thing to note here is that they go up to 4 and then the main thread ends, but the secondary thread is supposed to go all the way up to 10, well 9, but it just stops. Seemingly the main thread ended, and then all the threads associated with it, the spawn thread, also got closed off, so we didn't wait for it to finish. Okay, let's verify that. Oh, they got a 5. Why, how did they get a 5 and I didn't get a 5? That's awkward. Here was my confusion. I looked here, right? and I see 1, 2, 3, 4, and I see a 5. That 5 is not from the main thread. That 5 is from the spawned off thread, and that spawned off thread is supposed to go all the way to 10. So seeing a 5 every once in a while seems normal. Understood. Alright, so let's start from here. Note that with this function, the new thread will be stopped when the main thread ends, whether or not it has finished running. The output from this program might be a little different every time, but it will look similar to the following. So one, they note that the new thread will be stopped as soon as the main thread ends, which we stated, and that the output might look a little different every time. So this is why our output was different from theirs initially. Theirs actually made it to 5 in terms of the spawn thread. The calls to thread sleep forced a thread to stop its execution for a short duration, allowing a different thread to run. The threads will probably take turns, but that isn't guaranteed. It depends on how your operating system schedules the threads. In this run, the main thread printed first, even though the print statement from the spawn thread appears first in the code. And even though we told the spawn thread to print until I is 9, it only got to 5 before the main thread shut down. If you run this code and only see output from the main thread, or don't see any overlap, try increasing the numbers in the ranges to create more opportunities for the operating system to switch between threads. Okay, so what they mentioned here is that we use the thread.sleep to sort of give the opportunity for one thread to stop execution and another thread to start execution. This is all circumstantial because it depends on how your operating system schedules your threads. Some take turns, some may do some other type of scheduling methods. It really depends on your operating system. Anyway, they want us to experiment to change the numbers to give the operating system more opportunities to switch between the threads so we can see more numbers or less numbers depending on how you change it. That makes sense. I'm skipping over that. Waiting for all threads to finish using join handles. The code in listing 16.1 not only stops the spawn thread prematurely most of the time due to the main thread ending, but also can't guarantee that the spawn thread will get to run at all. The reason is that there is no guarantee on the order in which threads run. Again, based on your operating system, so very true. The spawn thread might not run at all. It happens. We can fix the problem of the spawn thread not getting to run or not getting to run completely by saving the return value of thread spawn in a variable. The return type of thread spawn is join handle. A join handle is an own value that when we call the join method on it, will wait for its thread to finish. In listing 16-2 shows how to use the join handle of the thread we created in listing 16-1 and call join to make sure the spawn thread finishes before main exits. Cool, so this is just something simple, a simple change. The only thing that really changed here is that thread spawn, right? It returns a handle, the join handle, and at the end or before main finishes, we make sure to call join on this handle and unwrap it. Which I guess if we return something and this doesn't return anything, so it should just be like a none or a nothing, a unit value in Rust maybe. But regardless, this is going to make sure we wait until this thread has finished. So let's write that up. Let handle equal that, and we see join handle here. That's nice. And we see the type it returns, which is just a unit value of nothing. And then down here we can do the handle dot join dot unwrap. Unwrap, no error. Yeah, I think that's spelled correctly. And then we should run this again and see all the way from 1 to 9 in the spawn thread. Here we go. Run. So yeah, now we get 1, 2, 3, 4, and then post 4 we just see the spawn thread. 4, 5, 6, 7, 8, 9. and it ran to completion, and then it exited out of main, which is what we want. Calling join on the handle blocks the thread currently running until the thread represented by the handle terminates. Blocking a thread means that thread is prevented from performing work or exiting. Because we put the call to join after the main thread's for loop, running listing 16-2 should produce output similar to this. And this is almost exactly what we saw. Almost. I mean, the order is a little different, but that's it. But one thing to note here is that it says calling a join blocks the thread that is currently running in. And by blocking, it means that it's not going to allow that thread to produce any work until the thread that the join is representing has finished. So if we move it, things should change. At least output should change. I think that's what we're going to do next. So two threads continue alternating, but the main thread waits because the call. So here, on the original example, the two threads continue alternating, but the main thread waits because of the call to handle that join, and does not end until the spawn thread is finished. But let's see what happens when we instead move handle that join before the for loop in main like this. So let's run that. Cut, paste, run. So in this scenario, we see that the spawn thread ran to completion, and then after that, everything after this line, which is the for loop, ran by itself, which is just a demonstration of how the blocking works. So where you put your handle that join matters. This over here. The main thread will wait for the spawn thread to finish and then run its for loop. So the output won't be interleaving anymore, as shown here. And they have the same thing we have. Small details such as where join is called can affect whether or not your threads run at the same time. Which is the takeaway. Makes sense. Using move closures with threads. The move closure is more often used alongside thread spawn because it allows you to use data from one thread in another thread. In chapter 13, we've mentioned we can use the move keyword before the parameter list of a closure to force the closure to take ownership of the values it uses in the environment. This technique is especially useful when creating new threads in order to transfer ownership of values from one thread to another. Okay, so what they're introducing here is the uses of move with our threads. So we saw in chapter 13 that we could use move to pass ownership from things in the main thread into our closure, or sorry, not main thread, we weren't talking about threads at that time, but in the outer scope into our closure. And we're going to do the same thing with closures, but incorporate threads. So seemingly we're passing variables that exist in this thread into another thread, and we're passing the ownership from one thread to another. Notice in listing 16-1 that the closure we pass to thread spawn takes no arguments. We're not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread, the spawn thread's closure must capture the values it needs. Listing 16-3 shows an attempt to create a vector in the main thread and use it in the spawn thread. However, this won't yet work, as you'll see in a moment. So what do they try to do? I see. So they have a thread, they have a vector, they have a spawn thread, and they're trying to access V in a new thread, which shouldn't work at all, just because it's two different scopes or two different locations. That I don't need to write. That should definitely not work. The closure uses V, so it will capture V and make it part of the closure's environment. And in most cases that is true. Because thread spawn runs this closure in a new thread, we should be able to access V inside the new thread. But when we compile this example, we get the following error. The closure may outlive the current function. but it borrows v, which is owned by the current function. And here they say that this closure may outlive the borrowed value. It's borrowed here. To force the closure to take ownership of v and any other reference variables, use the move keyword. I see. So what the error is actually stating is that the reason why this cannot be done is there's a possibility that this thread will outlive the borrowed value v. And the only way it can not outlive it is depending on where the handle and join is done, right? Because there's a possibility that this will never get ran. So that makes sense. Rust infers how to capture v, and because println only needs a reference to v, the closure tries to borrow v. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know if the reference v will always be valid. Listing 16-4 provides a scenario that's more likely to have a reference to v that won't be valid. And here's the example, right? In this scenario, they're just sort of validating what Rust's error is saying. If v were to be dropped before the handle join happens, then v is no longer valid when this is ran. If we're allowed to run this code, there's a possibility the spawn thread would be immediately put in the background without running at all. The spawn thread has a reference to v inside, but the main thread immediately drops v, using the drop function we discussed in chapter 15. Then when the spawn thread starts to execute, v is no longer valid, so a reference to it is also invalid. Oh no! To fix the compile error in listing 16-3, we can use the error message advice, which is force the closure to take ownership of v and any other reference variables using the move keyword. By adding the move keyword before the closure, we force the closure to take ownership of the values it uses rather than allowing Rust to infer that it should borrow the values. The modification in listing 16-3 is shown in listing 16-5. We'll compile and run as we intended. Alright, so this is what we care about. Move this over. I no longer need time duration. That has been taken out. And our main is a lot different. Oh, no. We are here because of the move. So again, just going through it. We have a vector. We have our thread. And we're moving the items that are used in the thread into the thread, or into the closure, which is handled in another thread. And then we're calling join afterwards. As such, v is no longer, the ownership has been changed, so v no longer exists in the scope. At this point, v is gone. But this should run. Here's the vector, and this was printed out in the scope, in the new thread. Sorry. What would happen to the code in listing 16-4, where the main thread called drop, if we use a move closure? Would move fix that case? Unfortunately, no. We would get a different error because what listing 16-4 is trying to do isn't allowed for a different reason. If we add move to the closure, we would move v into the closure's environment, and we would no longer call drop on it in the main thread. We would get this compile error instead. And so here what they're just stating is, I can show you the code, right? If we did drop here, v, this is silly because v is no longer in the scope. We moved ownership of v into the thread, and thus once the thread ends, the v should be dropped automatically. Thus we cannot drop here. This would be a, what was it, double free error, right? So no, that can't happen. And the error that they will show is this. Actually, I'm not even sure that's the error they'll show. Let's validate that. Drop v. And that's more or less what they showed. Yeah, it was moved into the closure. Variable has been... Actually, I can't even see all of it. Make this big. Moved into the closure. Variable moved due to, because it was in the closure. Variable is used after it's been moved. So yeah, what we expect. More or less the same what they have here. Yeah. Oh, this is the end of the section. Huh. So last paragraph. Rust ownership rules have saved us again. We got an error from the code enlisting 16-3 because Rust was being conservative and only borrowing V for the thread, which meant the main thread could theoretically invalidate the spawn thread reference. By telling Rust to move ownership of V to the spawn thread, we're guaranteeing Rust that the main thread won't use V anymore. If we change listing 16-4 in the same way, we're then violating the ownership rules when we try to use V in the main thread. The move keyword overrides Rust's conservative default by borrowing. It doesn't let us violate the ownership rules. With a basic understanding of threads and the thread API, let's look at what we can do with threads. That is the end of this video. I'm looking forward to figuring out what we can do with threads. I'll see you next time. If you enjoyed the video, like, subscribe. Aside of that, peace.